Hello, my name is Margaret Wooldridge, and I'm excited to be presenting to you Meeting the Moment, Reducing Methane Emissions and the Need for Better Diagnostics. I want to start by thanking my co-author, Jenna Stolzman, who is this wonderful graduate student working with me at the University of Michigan, and she has done a fantastic job on the experiments we've conducted in this area, and she's been a real pleasure to work with on the paper that supports this presentation. I also want to take this opportunity to thank the wonderful people who have put together this amazing conference. In particular, I want to thank Bassam and Jose for the opportunity to present on this topic. They have been incredibly supportive throughout this process, and I really appreciate the kind invitation they gave me. I also want to thank Tiziano for all his work and all of his team's work on hosting this conference. I know in particular how challenging it is to put on something of this magnitude and how much work it takes from so many people. So thank you very much to you and your entire team. And lastly, I want to thank Renee and Gabriella for their help walking me through the process of getting my presentation and my materials to the Combustion Symposium. They were amazing, and I know it takes a village to really put everything together. And lastly, of course, I need to thank all the attendees and the participants. Of course, we wouldn't be here without all the support of the members of the Combustion Institute, and I really appreciate your taking time to listen to and watch this presentation. So I'm going to start my presentation with a brief outline and stating my objective for this presentation. Specifically, I am hoping that everyone in the audience gets a chance to learn something new. And so I've started with a very intentionally broad discussion and contextualization of methane emissions. So this may be quite familiar to some of you, and some of the topics within the presentation might be quite familiar to people where this is your expertise and maybe your research focus. But I'm hoping that there is at least some portion of the presentation materials that is new to everyone in the audience. So that gives you the context for my outline, where we start with an introduction of methane emissions and then move to the specific application that we're considering for mitigating or reducing methane emissions, and that's specifically flaring. And I'll introduce the state of the art in terms of experiments, observations, and then at the end of that conversation, I want to leave you with some key takeaways for both flare emissions and more broadly for methane emissions. So that's the way my presentation is framed, again, to start broadly and then focus quite narrowly and then expand back out again at the end. And again, hopefully that gives something for everybody, something new for everyone to learn, and hopefully you'll find it entertaining and it tells a good story. So I'm certain our audience is quite knowledgeable about the role of CO2 in the atmosphere, and in particular the way CO2 plays a role in climate change and global warming. Perhaps fewer of you may be familiar with the role methane plays, and so that's what I wanted to discuss next. So in this figure, you can see we've got the methane concentration plotted as a function of time as reported by the NOAA observations. And what we see is this steady increase in methane emissions. And then in particular, we also see an increase in the rate of methane emissions in the more recent decade. So there are a few key facts that we want to take from these data. One is that the current methane concentration in the atmosphere is about 2 parts per million. And I do want to take this moment as somebody who teaches thermodynamics to say, I understand that the parts per million unit is a unit of mole fraction or volume fraction and not concentration. But this is typically the way it's reported with the atmospheric scientists, so I'm going to stick with their convention. So we'll refer to mole fraction as a concentration. Although again, as a thermodynamics professor, that's hard for me. So we want to, again, key takeaways. One is that the methane concentration is about 2 parts per million in the atmosphere, and the rate at which the methane emissions are being released into the atmosphere has been steadily increasing over the past decade. So those are two really important things for us to understand. So methane emissions are increasing, and now we want to understand why that's such a bad and somewhat scary thing. So in this figure, what we have here are several model predictions for the increase in surface air temperature relative to a baseline of around 1900, the year 1900. And these are model predictions based on different scenarios, and they're different scenarios considering methane mitigation. And the top line here, the solid red line, is essentially the increase in surface temperature that we could expect if we have no mitigation of methane emissions at all in the next several decades. And then so that's the solid line. The dashed lines refer to model predictions if the model includes carbon climate feedback. And so I'm going to explain what that is here in just a moment. But again, the red lines here are essentially no mitigation of methane emissions. And then the rest of the family of lines, as we move down, show what would happen if we take efforts to mitigate or reduce the amount of methane emissions that are released into the atmosphere. And the different colors of lines refer to the time at which we start doing methane mitigation. And so this direction of this last arrow here, it shows you that the increase in the average surface temperature decreases as we start methane mitigation earlier. So in other words, we see lots of benefits associated with this, lots of benefits associated with methane mitigation looking at these model predictions. We see both that the peak surface air temperature anomaly, or the increase in surface air temperature, is decreased as we mitigate methane emissions, as well as the longer term surface air temperature. So both the peak, that kind of overshoot, as well as a longer term temperature decrease with methane mitigation. And the earlier we start methane mitigation, the better the impact, the more reduction in the temperature anomaly that we see. Now, some other really important features that we want to take into consideration here. First of all, why is methane play such an outsized role on the surface air temperature? And that's because methane, as we would expect, again, in this audience, we're probably very aware that CO2 is an infrared absorber and methane is an infrared absorber. And it's a very effective infrared absorber. And when we rank the global warming potential of methane, we see that it's 84 times higher than that of CO2 in the 20-year timeline. So in other words, in the shorter time frame, methane is more potent as a greenhouse gas than CO2 is. Now, that doesn't mean we should not mitigate CO2 emissions. What it means is that we should mitigate and reduce both CO2 and methane emissions. And methane emissions has this really outsized potential impact. And model predictions, like the ones that I'm showing you here, show that not only will it have the significant benefit, but the faster we start with methane mitigation, the more benefit we see. The other last kind of key takeaway I want us to see from this plot is that notice that these model predictions all show essentially we're going to come up to and potentially pass a 2-degree surface air temperature increase. And that has really significant impact that's pretty devastating around the world. And so that number of 2 degrees, we've often heard 1.5 is what we want to hold it to. Notice that none of these models hold us to less than 1.5 degrees. But with methane mitigation and early methane mitigation, we can hold to potentially less than 2 degrees. And that's a huge incentive for helping us, a huge incentive to mitigate methane emissions. So where do we start? We want to mitigate methane emissions, so the first thing we need to know is where are the sources and what are the sinks for methane. So this figure on the right shows you schematically the 4 major categories that are sources of methane emissions. So they include fossil fuel production and use, agriculture, and waste, which are generally considered 2 separate categories. And then these other categories on the kind of in the middle of this schematic are the natural sources of methane. So there are a significant number of natural sources of methane emissions. So group these together and we get the total emissions of methane. And in particular, this graphic is showing the average values over the past decade. And all units are teragrams per year. And we can see the average is about 580 teragrams. On the right-hand side of the schematic, what we see are the sinks for methane emissions. And this is where methane differs significantly from CO2. Methane is essentially only removed from the atmosphere by reaction in the atmosphere. And that reaction is predominantly with OH, the hydroxyl radical. And so this is the source of that carbon coupling that we saw in the previous modeling. So methane is only removed from the atmosphere by reaction with OH. So if you decrease the amount of methane that you release to the atmosphere, you essentially allow that OH to react with other methane. And so there's an amplifying benefit associated with mitigating methane emissions. So again, if you reduce the amount of methane emissions, you essentially leave more OH in the atmosphere to react with other methane and other species in the atmosphere. So that's where we get this carbon coupling and this added benefit associated with not releasing methane emissions. Now, the other thing that I want to highlight about this figure is that these data come from essentially 2 categories of sources. They're bottom-up sources and top-down sources. So essentially, bottom-up sources are from inventories that are reported to places like the United States Environmental Protection Agency. So their industry and organizations are required to report their methane emissions, and then they're required to report the sources of their methane emissions, and then based on the policies of the EPA, there are emission factors that are then used to determine the amount of methane associated with those activities. So the methane emissions aren't measured directly in most cases. Instead, what's measured, for example, are flow rates in your natural gas pipeline and things like that. And then emission factors are applied in order for them to develop a bottom-up inventory. Top-down inventories use aerial surveillance, satellite surveillance, and so they essentially do measurements from the atmospheric side of the equation. So another key point that we want to take away from this figure is that we see that the values for the sources and sinks are not matched. So in other words, the global methane budget is not balanced. And we knew this already from the first figure that we saw. Essentially, methane emissions are increasing. So we know that the methane emission sources are larger in value, in absolute value, than the methane sinks. Okay, so let's unpack the sources of methane emissions a little more. We already identified in the previous slide that the fossil fuel industry is a significant source of methane emissions. And so that's the topic that I'm going to dive into more and focus on for the remainder of the presentation today. So just again, for context, I've got emissions data from the US as reported to the Environmental Protection Agency to kind of show you where this fits in the scope of the overall greenhouse gas emissions. So we see that, again, the majority of the greenhouse gas emissions are from CO2. Methane is essentially 10% of the greenhouse gas emissions in CO2 equivalent in the US. And so then we say, okay, what are the sources of methane? Again, we already identified the general categories in our previous slide. And here, more specifically, we see that natural gas and petroleum systems are a little less than 30% of the emission sources in the US. Other countries, in other countries and other continents and other locations, these percentiles will shift slightly, but in general, the 2 largest sources are going to be your agricultural industry and your fossil fuel industry, and then waste. Specifically, for those who may not be aware, enteric fermentation, that's the methane that's emitted due to the digestive system associated predominantly with ruminants, like cows and pigs and horses and things like that. So the bottom-up inventories tell us that the fossil fuel industries are sources of methane emissions, and they give us specific amounts. But as I mentioned, top-down surveys and studies have shown different results than the bottom-up inventories. And the results I'm showing you in this figure and in the next figure were pretty impactful, because this study, which was conducted in part by a colleague of mine from the University of Michigan, Eric Court, showed a significant difference in the amount of methane that was being emitted specifically from flares. So what you're seeing on the left here is a map of the regions where they did their sampling, and they did a combination of satellite imaging, and those are the data that are shown as kind of the red triangles, the VERS data, so those are satellite methane imaging. And then the fuel blue dots, they're kind of hard to make out here, but they're within these different shaded regions, the yellow, the teal, and the kind of purple shaded regions. They did flyovers, so aerial gas sampling campaigns. And they found a few things that were really significant. One is those 3 regions of the United States corresponding to the Bakken, Eagle Ford, and Permian development regions, where they're extracting those fossil fuel resources, are the majority of the flared gas volumes in the United States. So those small regions actually account for the majority of the flared gas volumes. The EPA again, determines what the emission factors are associated with different technologies. And for flares, the EPA has specified that if you are operating an EPA compliant flare, the combustion efficiency and destruction removal efficiency, and I'll formally define those parameters in just a few moments, should be over 96.5% and over 98% for the destruction efficiency. So again, if the flares are operating using EPA compliant technology, the combustion efficiency should be over 96.5%. Well, the results of the study by Court and Plant and co-workers showed that the destruction removal efficiency for methane was in fact lower than the 98% specified by the EPA emissions factor. And so they observed, if you see on the left-hand side of this graph, you see the observed mean value of the methane destruction efficiencies for the different regions, with the average shown in yellow. And then what they also observed, which is really important during this campaign, this flyover and airborne sampling campaign, was that some of the flares were in fact unlit. And so they were essentially directly venting methane or other gases to the atmosphere. When you take into consideration those unlit flares, you then you further reduce the effective destruction efficiency for methane to values that are between 87 to 94%. And you may think, well, let's say 94% isn't that far from 98%, but when you consider the flared volumes associated with flaring in the United States, that equates to essentially a difference of about 0.5 teragram per year of underaccounted methane emissions. So this is significant. It was a huge impact when the data were released, showing that, again, flare efficiencies were much lower than what people were expecting. Under certain circumstances, it looked like the equipment wasn't even working. And so this presents both an opportunity and a challenge. So this is what we'll be focusing on, which is how can we improve, first, our understanding of the flare combustion efficiency performance. So what are actual data based on measurements from the bottom up. And then further, once we get this knowledge of what the flare efficiency is as a function of broad operating parameters, how might we improve it if it is below the combustion efficiency of 96.5%. So let's learn a little something about flares. Flares are safety devices. So they can be generally divided into two categories in terms of the technology. They're either considered assisted, where you assist the combustion using either steam or air that's directed into the combustion zone, or you have non-assisted technologies where essentially the flare has no augmented flow or mixing from external power flow sources. They're used in, again, fossil fuel industry, upstream or production, like we talked about. The majority of the emissions from the fossil fuel, the majority of the methane emissions from petroleum and natural gas are from the production or the upstream portion of the industry. But they're also used in midstream and downstream, and this is important. So downstream, for example, refining, and flares are also used in landfills and in agriculture. Because there's this broad spectrum of applications and uses, there's a broad spectrum of compositions that can be used in flares. So we want to pay attention to that. And we also want to recognize, I think this is important to state here, is that while I've been focusing on methane emissions, obviously flares produce CO2. They can also produce or emit volatile organic compounds, ethane, propane, nitrogen oxides, sulfur oxides, and soot emissions. Generally speaking, if we improve the performance of a flare, improve the combustion efficiency, we will also reduce the efficiency of those criteria air pollutants. So let's define the combustion efficiency. The combustion efficiency is essentially how effectively did you convert the carbon mass in the flare gas into CO2. And it's defined on a mass flow rate basis. The destruction removal efficiency, sometimes called just the destruction efficiency, can be for the total hydrocarbons relative to the total hydrocarbons of the flare, or it can be for a specific species. Like I've been talking about methane, but I'll move back and forth between total hydrocarbon destruction efficiency and methane destruction efficiency. And the definition, again, is this ratio of how well did you convert that particular species that's in the flare gas to CO2. So as you would expect, combustion efficiency and destruction efficiency can correlate well with each other, right? And where you have high CE, you'll generally have high DE. It's really easy for us to define them. It's a lot harder to measure these species. And so if we look at the schematic of kind of the basic components of a flare, which are shown on the left-hand side of the screen, we see that kind of the basic components would include liquids knockout, because we don't want liquids to get to our burner, so we want only gas-phase species to get to the burner, the flare burner. And then we have the flare stack, which includes a flame arrestor, and then we have the flare burner, which is at the tip, or the flare tip, or flare burner, I'll use those interchangeably, where we're actually going to burn the flare gas. And these systems are generally non-premixed diffusion flames. They're going to have a little bit of premixed through some cleverness in terms of the technology design here, but generally these are diffusion flames. All flares in the United States are required to have a continuously operating pilot flame. And so they have to have a source of an ignition source and a pilot source that are continuously operating and that help stabilize that combustion system at the flare tip. And as you're seeing in the schematic here, the methane emissions range from essentially the concentration that you might have for natural gas, where it could be like 96% methane, to, at the tip, exiting the tip of the flare, to essentially a few parts per million if you have a really high combustion efficiency flare. So that means if you're trying to detect the amount of methane that's being produced by your flare, you're going to have a really sensitive analytical device, something that can see above the 2 ppm atmospheric baseline to detect the single digit to maybe tens of parts per million of methane. And the further away you are from the plume, the more dilute that plume from the tip of the, let's say, the visible flame, the more that plume is going to mix with the gases, and the detection of those combustion products is going to be harder and harder because they're going to be smaller and smaller amounts. And so the insert here shows you, essentially the scale that you would have associated with the mole fraction of methane, for example, as you move away from the tip of the luminous tip of the flame. Of course, the amount of flare gas that you put into the flare is also going to dictate the amount of methane that you get out, and so flow rates matter. Now, those are the in the previous slide, we gave the general definitions for CE and DE. The catch is measuring mass flow rate, particularly in the field, is a really difficult parameter. So, and we can kind of see why that would be challenging in the schematic in the upper left here. Specifically, we have the flare gas. The flare gas flows into the burner, and then it has combustion air that mixes with the flare gases in order for us to have combustion. And then those products are then mixed with the ambient air, causing additional dilution. And so our plume actually consists of, both the flare gases and, of course, all this air that has been entrained and mixed with our combustion products. And these mass flow rates are really difficult to measure. And so instead, what we'd like is to define the CE and the DE in terms of parameters that are more accessible to us as experimentalists. And specifically, that means typically converting these definitions to mole fractions, which are more easily measured using a number of different technologies. And so you see those conversions here. I don't want to go to the details of like how this, the assumptions that were made and how we get from those previous equations to these two. Instead, what I want to highlight to you is just a few things that, again, might seem quite intuitive. One is we need to measure the CO2 that's produced by the plume, but we need to differentiate it from the CO2 that's in the ambient environment. So you need to be able to measure both those two quantities accurately. We also need to measure, again, methane, if we're interested in particular, the destruction efficiency of methane, both in the plume and in the ambient. And we'll also need to measure CO, a primary product of combustion. And if our flare is doing pretty poorly, we're going to need to know the other trace hydrocarbons that are going to be formed. So again, we have a number of species that we need to measure. We can get accurate efficiency measurements using mole fractions, but if we want to measure emissions on a rate basis, we are also going to have some sort of flow rate measurements, which might be something that we could do in terms of instrument. So might mean we instrument the flare gas itself, and we put a flow meter on the source of the flare gas. And that's a primary way that you would quantify, move from the percentile space to the absolute value space. So what do we know about flare performance? Most of what we know has come from these really important foundational ground-based flare studies. There's a lot of information on the screen, and I don't want to look at all of it. I just want to highlight a few features. One is most of these studies were using steam or air assist flare technologies. The other is they cover a broad range of heating values, and this comes from the broad range of fuels that were used. And I'll show you some data on the fuel compositions here next. The other is to note that the flare gas flow rates that we're talking about in these studies are huge. Note that the common unit for these flares for the flow rates is 1,000 standard cubic feet per day. So these are huge flare systems physically and based on their flow rates. So let's look at the compositions here. Again, there's a lot of information on the screen, and I just want to highlight kind of a couple of comparisons here. So the data on the left side of the screen represent those foundational studies. So those are essentially showing you that those studies really covered a pretty diverse mixture of gases in the flare gas. And you can compare that, like Tulsa natural gas is shown as the third bar from the left, and you can see, natural gas is mostly methane. So the gas composition that was used in those studies is really more typically associated with that of refineries and not that associated with natural gas or perhaps upstream production operations. So what about the diagnostics? What are the typical ways that we would measure the emissions from these flare systems? Some of these were used in those foundational studies, some were not. But essentially we have two categories of methods for measuring those emission products, the emissions from our flares. We have extractive technologies and we have non-intrusive or remote technologies. Extractive technologies are just what they say. I'm sure most of us are familiar with these, where essentially you take a gas sample and then you have a suite of different gas analyzers and analytics that you can use, from gas chromatography to NDIR, cavity ring down spectroscopy. So again, once we extract some plume gas, we've got lots of different ways that we can determine the quantity of CO, CO2, methane, and other species that we're interested in. With respect to remote imaging, which is super important when you're talking about stacks that are 40 feet high in the air, the technologies are typically based on some form of spectroscopy and more specifically infrared spectroscopy, which makes sense because we know that our methane, CO2, CO are all infrared active. So these are the primary methods. You can see the different time scales, temporal and spatial fidelity associated with each of them. There are pros and cons to each of them. None of them is perfect, and they all do some sort of averaging, either temporally or spatially. So our foundational ground-based flare studies, our bottom-up studies, were incredibly important because they set the standard for understanding flare performance. They were expensive and difficult experiments to do, and we want to give huge kudos to the scientists and the researchers and the technicians that executed those experiments. But, because there's always a but, they necessarily covered a limited parametric space. For example, again, we know that they focused on steam and air assist technologies. They primarily considered what we would call downstream or refinery type gases. And there's little information on low flow, non-assist, or essentially utility flares. But we learned a lot. And so that's what I want to share with you next. So these figures show us some of the really important takeaways from those foundational flare studies. They helped us identify essentially when do we get high efficiency and what leads to low efficiency. What are some of the parameters? And again, many of us in the audience might find this somewhat intuitive, but again, hopefully it's new for some people. So let's start with the air assist data that's shown in the leftmost panel here. We see the combustion efficiency as a function of the excess air stoichiometric ratio. So for the air assist technology, we have a compressor or blower or a fan that allows us to push air into the combustion zone. And this excess air ratio represents how much excess air we're putting into that combustion zone. And what we can see is a clear trend that if you increase the excess air, you decrease the combustion efficiency. So somewhat intuitively, we want the right amount, just the right amount of air at the burner tip. When we look at the steam assist data, so the middle panel and the rightmost panel, again, we see the combustion efficiency in the middle panel as a function of the steam to vent gas ratio. So this is analogous to the excess air ratio that we had with the air assist. We see a similar trend where if you add too much steam to the burner tip, we see a significant decrease in combustion efficiency. Steam is only going to be an option for improving the combustion performance of our flare if we have a boiler and some other power equipment on site. So again, both air and steam assist have some site location restrictions associated with them. So you're going to have power. Again, for steam, you're going to need a boiler. You might think, well, why would you ever over steam or over air your flare? Well, the reason we add those features to a flare is primarily to reduce the soot emissions that are quite visible from these flares. And so there's some concern that people might oversteam or over-air, flare operators might oversteam or over-air in order to reduce the visible soot emissions, because that's what the neighbors will complain about. It's also a regulated criteria pollutant. So you can see that there's this balance between good combustion efficiency and, unseen in these data, the particulate emissions. The rightmost panel on this slide shows you the combustion efficiency as a function of the net heating value in the combustion zone. So this takes into, again, the consideration of dilution and mixing with air assist or steam assist. And this shows perhaps the most clear trends, seems somewhat more universal compared with some of the other trends, where as we increase the heating value, the combustion efficiency is quite good. So we exceed that 96.5% combustion efficiency that is the EPA standard for their emissions factor. So again, we see really good performance if essentially the flare gas has enough energy content in it. The foundational flare studies also gave us really pivotal information on understanding the relationship between combustion efficiency and destruction efficiency. Now in this figure, the destruction efficiency data are for all hydrocarbons. So these are from studies from, again, about over a decade ago. And methane was less of the primary focus that it is now. And this figure shows you there is clearly some correlation between the destruction and combustion efficiencies, particularly as we get to high performance. So as we get to high efficiencies, the general rule of thumb was the destruction efficiency was about 1.5 plus the combustion efficiency value. But you can see that as we have poor performance, if we get into these regions where the combustion efficiency is less than 80%, the correlation is not anywhere near as transparent or obvious. And we see a lot more scattered. But generally speaking, if your combustion efficiency is good, your destruction efficiency is going to be good. So we saw a lot of scatter in the previous data that we looked at, both for combustion efficiency and destruction efficiency, and for steam assist and air assist as a function of some of the key combustion parameters. And so you might think these data are particularly well suited for machine learning algorithms and model development. And in fact, they are, because one, we have a lot of data points under a lot of operating conditions. And so we can identify kind of key attributes that we would expect to be important in terms of developing machine learning models, things like Reynolds number, heating value in the combustion zone, right? These would all be somewhat intuitive to us, and we can take those features or characteristics of the data, we can feed them into machine learning algorithms. We actually get really, really good performance in terms of reproducibility of the combustion efficiency and destruction efficiency for a pretty broad range of conditions for air assist and steam assist flares. So if you can make it out there, it's kind of an eye test, but the R-squared values for the air assist and steam assist machine learning models are over 90%, so pretty good. But when we go to non-assist flares and consider the data, we get values that are much lower, R-squared values that are much lower, so around the order of 70%. Now this is exciting because you might think, well, close the book, we've done it in terms of air assist and steam assist, we know what works. The challenge is, while that would be, the machine learning models are really helpful for things like if you had like an active control system you might want to design, or if you want to identify best practices, they're not predictive and they're not terribly scalable. And so that makes it quite challenging in trying to address these low efficiency points. Like trying to identify what are the key physical attributes is challenging based on machine learning models. So they're good in that if you design a flare and you test it, you can take those data and put it into a machine learning algorithm and say how consistent is it with previous performance. But the converse is not also true. You can't really use machine learning models to extrapolate and scale or design a flare burner. So let's look a little bit more at these non-assist flares, because we know that they're a challenge, both in terms of machine learning algorithms and based on the data that we see in those foundational flare studies. And now I'm showing you data from some of the results in our laboratory and some of the work that we've done in collaboration with Southwest Research and STEFIS, and some work that has been done by Peter Gogolek using a really impressive wind tunnel facility. And so on the left panel here, what we see is the combustion efficiency as a function of crosswind. And what we see is as the crosswind increases, we see a significant decrease in the combustion efficiency. Now, these non-assist flares are essentially the theoretical combustion, or the fundamental combustion researcher's dream, because it's just a pipe with a fuel burning with a crosswind. So it's essentially a jet and crosswind, a jet and crossflow. So again, it's pretty fundamental. The experiments are a bit more challenging because of the scope and the scale, but you would think that we would be able to extrapolate from different sets of conditions, in particular from, let's say, as a function of the diameter of the pipe. And so what you see on the left here is now we've got the combustion inefficiency. So this is 1 minus, or 100% minus the combustion efficiency percent. And then an attempt to reconcile all these data sets through a scaling factor. And that scaling factor has been proposed by Peter Gogolek, and some other folks have proposed some other scaling factors. And you can kind of intuitively see what we're trying to capture in these types of scaling laws, but you can also see that we're not capturing it, that essentially the data have enormous scatter, and we can see when we compare the data sets that are between turbulent crosswind and non-turbulent crosswind. So this is where Peter attempted to laminarize the wind tunnel wind source, that we see huge scatter in the data. And our data here, I'll show you the experimental setup is in the next slide, is essentially just a blower and a single pipe. And we can see we're within the scatter, but the power factor does not reconcile or collapse the data. And Peter's data span a range of different pipe sizes, and we see that, even when we take into consideration things like the pipe diameter and some of the other physical attributes that we'd expect to potentially allow us to kind of collapse the data, we don't actually achieve kind of a consensus scaling law. And so we're kind of in a difficult position with these utility kind of pipe flares, in the sense that they don't scale well based on the data that we have so far and the scaling methods that we have so far, and they're not terribly interpretive or well interpreted by machine learning models. To understand a little bit more clearly why we're not able to collapse our utility flare data, and just to understand the general challenges associated with doing flare emissions experiments, I've got some data here that are from our recent test campaign at Southwest Research in San Antonio, Texas. And what you're seeing on the left are videos of the actual experiments as they were being operated. And the left-hand side of each video is the blower. On the right-hand side, you can see a 10-foot by 10-foot hood that was used to collect the gases from the flare plume. You can see these are for some pretty significant crosswinds. This is about 22 mile-per-hour crosswinds for each of these. The top panels represent natural gas. The bottom panels represent a blend of propane and natural gas, so a higher heating value fuel. And the scatter plots that you see in the data show you the combustion efficiency of different designs of flares. And the basic 3-inch pipe is shown as these blue squares. And so what we see is that the basic 3-inch pipe, and for all designs, as you increase the crosswind, you decrease the combustion efficiency below the EPA emissions factor. We do see a significant improvement in the combustion efficiency when we have a higher heating value fuel, which again is consistent with what we would expect based on those foundational flare studies. So some positive outcomes at some conditions, combustion efficiency is really, really high, but at other conditions, not so much. And we can kind of identify the pain points or pinch points based on experimental data like these. This video is just to emphasize, it's from the same setup that we just saw in the previous slide, but I've used some slow-mo here to give you some better indication of some of the transients that you see in these flare systems. And I think this is super important for us to recognize, is because although there is a fixed emission factor and we report a combustion efficiency for a flare, the reality is the devices are not steady state, steady flow. And it's not just in our experimental setup here, but just overall, your flare gas composition will change due to the age of the application, the time of year, the type of operations that are being conducted. And then it's in an environment which of course is also highly dynamic, right? So Mother Nature is highly variable and doesn't tend towards steady state, steady flow. So again, these systems are complex to describe, and even in this somewhat controlled environment that we created for these flare testing, there's still some variability that's somewhat beyond our control. The other thing to recognize is that we were, again, kind of had the opportunity here where we could put a hood that could actually collect essentially the entire plume, which is advantageous in terms of trying to do a global combustion efficiency measurement. But they're huge flames, like these flames, this is a really low flow flare system that we studied. The full scope and scale of flares covers a really incredible range of flow rates, and the flames can be well over 10 feet, 20 feet long. These were relatively modest at something like 3 to 10 feet long. So they're huge flames, and where you do the measurement matters in terms of your interpretation of the emissions and how you assign destruction efficiency and reduction efficiency. So where does this leave us? Hopefully I've given you a chance to see some of the data that are pivotal to flare performance, given you a chance to maybe learn some new things about either the methane budget or about flare applications in particular. What I want to leave you with, though, are some pretty important takeaways and opportunities for this particular community, the Combustion Institute community. One is, we know that basic utility flares, or these non-assist flares, can have high combustion efficiency and high destruction efficiency. We know kind of where the sweet spot is. We also understand that in real world applications, they are probably not operating at those conditions. So this gives us an opportunity to try and understand bottom-up measurements and where are the sources, potential sources of discrepancy between bottom-up and top-down measurements. And specifically, this points towards an area where we are significantly under accounting for methane emissions from flares. Now, utility or these basic pipe flares, you might think, well, how important are they? They're generally associated with low flow, low flare gas volumes. And so if you see the graph at the bottom of this slide, you can see this is the distribution of flares based on flow. And what you can see is that tens of thousands of flares are in this category of low flow operation. So the potential for underreporting methane in this category by assigning an inappropriately high average combustion efficiency or destruction efficiency is high. The opportunity for there to be a significant underaccounting is high. So we need more data, though. We need greater understanding. Again, we can't test at all the parametric conditions that you might experience in the real world. And so I didn't have the time and opportunity either in this presentation or in the paper to really talk about the role of modeling and theory. but they are both absolutely critical to mitigating methane emissions from flares. We absolutely need modeling and theory to help us with scaling, for data interpretation, and to design, test, and build. So again, really important role for the modeling and theory communities. I did want to just highlight here an example of that. This is on the right. You can see a little animation of a large eddy simulation that was done by Ray Mohit, who is a graduate student working with Jesse Capistelletro, my colleague and collaborator on this project. And it shows you that we were able to actually reproduce flame blowout like we were seeing in some of our experimental observations. And so again, this will be really pivotal in helping us trying to understand where the pain points are and how to improve overall combustion performance. And as I mentioned before, a rising tide lifts all ships. If we can reduce the methane emissions from flares, there will be collateral benefits with other criteria air pollutants, for example, like volatile organic compounds, other VOCs. I also wanted to leave you with some key methane takeaways. So the challenges that we saw in terms of the transient behavior of the flare systems, the geographic distribution, the different technologies, all of that can be analogously applied to other methane emissions sources around the world. And so, there's a need not just for additional experimental data in diverse systems for flares, but also for these other methane emission sources. So I would encourage you to develop the technologies, the diagnostics, the analytics, the methods, and develop the methane mitigation technologies. We need both. And I'll close with the comment that monitoring, verification, and reporting of methane is urgent and timely. There are huge resources that are being put into these efforts addressing methane inventories, and in particular, we need solutions at all scales, from the laboratory to the pilot scale to the field scale. And the cost can have gradations here, where you can go from more expensive equipment like you might use in your pilot scale measurements, but we absolutely need low-cost emissions measurements that we can deploy in field settings so that we can gather more temporally resolved and more spatially resolved data. So there is an opportunity here for everyone. And again, the combustion community has been working on methane for decades, if not over 100 years, and we are well suited to bring our expertise and our resources to bear and really make a change in methane emissions. I'd like to acknowledge the generous support of the ARPA-E Remedy program at the Department of Energy at the United States. They've been amazing and wonderful to work with on this project. I also want to take this time to thank our collaborators on the FLARE project work that I've shared with you here today. At Southwest Research Institute in San Antonio, they've been just remarkable in helping us build new test facilities. They've been incredibly collaborative and supportive as we come up with new designs for how to implement this crazy equipment. And I also want to thank Steffes for all their insight and help they provided on flare manufacturing and the needs of the industry and the key stakeholders in the flaring community. And of course, thank you, the audience, for your time and interest in watching this presentation. For those who want to learn a little bit more, the references are listed on this slide. Thank you again.